Okay, everyone, so we're talking about topic 3.1, intermolecular forces. Just a heads up, I'm going to be moving pretty quickly through this, and so pause as you need, take lots of notes, make sure you ask me questions when you get back. There is a difference between intramolecular and intermolecular. So first reminder, molecular molecules are covalently bonded atoms. They're non-metals, okay? Molecules are non-metals, right? A non-metal bonded to non-metal, right? So non-metal atoms, and they are covalently bonded. Okay, now this structure of atoms covalently bonded, whether it's polar covalent or non-polar covalent bonds, that is a molecule. The intramolecular force holding atoms together inside of a molecule are those covalent bonds. Okay? And again, it could be polar covalent or non-polar covalent. Let's add the lone pairs onto this water molecule. So in this image here, we got two water molecules. One right here, one down here. And there is, in this case, it's a polar covalent bond that's holding the hydrogens together with the oxygens in that molecule. These are relatively strong. They're not as strong as ionic bonds, but they're quite strong. Now, if I have a molecule, and look, I have right here. Here's one of the water molecules, here's the other one. And so this is the covalent bond that's holding these together, and it's pretty strong holding it together. But it turns out that there's also an attraction between the molecules, not inside, but between, okay? And this in-between attraction are intermolecular forces. Intra, within, inter, between. Okay, between molecules. Nice. Now, IMFs, intermolecular forces, are not as strong as intramolecular. And IMFs always stands for inter, not intra. So whenever I say or you see IMF, it's the intermolecular force. It's between. And these are the different types of IMFs that you're going to have to be aware of and you're going to need to be able to identify. So you can tell, you need to know when it's an ion and you need to know when a molecule is polar or non-polar. So quick reminder about polar or non-polar molecules. Okay. If something throws off the symmetry of a molecule, this has 4 electron domains, 1, 2, 3, 4. When one of the electron domains is different than the other ones, that is asymmetry. And when a molecule is asymmetry, it's a polar molecule. But when the electron domains around the center are the same, then it's symmetrical. This has 2 electron domains. They are both the same. They're both bonded oxygens. That's symmetrical, so this is a non-polar molecule. All right, lovely. And the other thing I want to tell you is diatomic molecules, like N2 or H2 or F2, are always symmetrical as well. They're always non-polar. And then the last thing I want to remind you of is hydrocarbons. A molecule that contains any number of carbon and hydrogen, but it's only hydrogen and carbon. It doesn't matter what the structure looks like. If it's only hydrogen and carbon, it can be as big as it wants to be. It will always be non-polar. Okay? Now, what if the two things that are interacting are an ion, like maybe magnesium 2+, and a polar molecule? We have this ion that is completely positive, and then we have the asymmetry of this molecule that's making one side of it partially negative and other areas of it partially positive. And so there's going to be an attraction between these. Here's my positive ion, and it's going to be attracted to this like negative end of the molecule here. And this attraction between this molecule and this ion is a type of IMF. And the type of IMF that it is an ion dipole. Now the reason why they call it, the ion part makes sense, it's an ion. The reason why they call it dipole is because only polar molecules have dipoles. I'm going to say it again. Only polar molecules have dipoles. Dipoles are regions. Think of it like a magnet. Because we're asymmetrical, that means that there's a region where the electrons might spend more time. There's like a negative region, and there's a positive region of this molecule here. Those are dipoles. Now here's my cation, and here's my negative dipole. And so there's an attraction between the positive ion and the negative part of this molecule. There's not an attraction between the negative end of the molecule, or sorry, the positive end of the molecule and the positive ion. They repel. Now there's going to be some questions about these ion dipoles, and it's going to specifically deal with the charge of the ion or the radius of the ion, okay? So when it comes to ions, and this is true whether it's an ion dipole, an ion attracted to a polar molecule, or lattice energy, like the attraction between ion and ion. The first thing that you should always look at is charge first. Okay, charge first. The greater the magnitude of the charge, the stronger the IMF, or the attraction between the ion and whatever it is. So when the charge is bigger, the attraction is stronger. It's directly proportional. Look at this example. We have magnesium 2+ and we have lithium plus. So because this is a 2+ and this is just a 1+, that's why this attraction is stronger and this one is weaker. Now, let's say that the ion charge is the same. They're both a +1 or they're both a -2, whatever. Now we're talking about ion radius. Okay, ion radius. Only if the charges are the same, we look at the radius, okay? And when the radius is bigger, then we have a weaker attraction. So directly proportional for charge, inversely proportional for radius. Now this makes sense because look at the distance between the small one and this molecule, and then look at the distance between the big one and the molecule. By the fact that the ion is bigger, it means that it's going to be further away from that molecule. And we know that when the distance is big, the attraction is small. And so if they have the same charge, then we look at the radius. The larger the radius for the ions, the larger the radius, the weaker the attraction. So that's why smaller radius is stronger attraction, larger radius is weaker. Okay, let's save this example for class. Remind me to highlight this point. Okay, let's keep going. So there are two types of IMFs that deal with ions. We have ion dipole, and then we have something called ion-induced dipole. Okay. Now, dipole we reserved for polar molecules. Let me go back. Dipole we're going to reserve for polar molecules. Induced dipoles we're going to reserve for nonpolar molecules. So if it's an ion-induced dipole, that means that we have an ion. Maybe let's go with oxygen as an ion. So it's oxygen, it's a 2-, okay? And we have a nonpolar molecule like CH4. Okay. So, 2 reasons why this is nonpolar. First is it's symmetrical. It has 4 electron domains and they're all the same. Second reason why it is nonpolar is because it's a hydrocarbon. It's a molecule that's made up of only hydrogen and carbon. So we have an ion and we have a nonpolar molecule. And there will be an attraction between them. It's relatively weak, but there is an attraction there, and that IMF attraction between them is the ion-induced dipole, because it's an ion and it's a nonpolar molecule. Now the way that this even works is pretty crazy. So it's like we have this thing that's negative, right? And this molecule has a bunch of electrons in it. So imagine the electrons. So we got this like negative thing, and then we have this molecule that has electrons in it. And if we bring this negative thing over to this molecule with electrons, then the the negative thing, sorry, leave that as a negative, not a positive. This negative thing actually like pushes the electrons away, and we induce a dipole. We cause it where we've pushed the electrons over here, and so for a moment in time we get a slightly negative side, and then we get a slightly positive side. And so now the negative thing is close to that slightly positive side, and that's the attraction between them. And it doesn't exist really long. Like, it'll go away and then it'll come back and go away and come back. But that's what our ion-induced dipole is. Now our next type of IMF is dipole-dipole, and I bet you're getting the gist of it now, that we reserve dipole for polar molecules. So this is a polar molecule, and there's an attraction to another dipole or a polar molecule. So it's a polar molecule and a polar molecule. Okay, please, please do not forget that water is a polar molecule, because what happens is that when we draw the Lewis dot structure, 2D, it kind of looks symmetrical, but we know that it actually makes this tetrahedral kind of shape. And that this tetrahedral shape, I don't have a model close by, that's okay. This tetrahedral shape has the hydrogen and the oxygen, but then this is a lone pair over here and this is a lone pair over here, that it is not directly across from each other like this. It's almost better to draw water as this bent molecule, because it will actually be bent. That's the electron geometry. And then the lone pairs are going in and out of the paper, but they're over there. Okay? Now, these lone pairs are definitely a negative region, and this oxygen is more electronegative than hydrogen. And so we have this permanent dipole. It's kind of like a magnet, where this end of the molecule is going to be negative over here, and the hydrogens, electrons spend less time with the hydrogens, so they stay, the electrons spend more time over here, less time over here, and that makes positive ends. So we got this magnet that has a negative end and a positive end on it. And what happens when one magnet, or a polar molecule, gets close to another magnet, or a polar molecule? Then there's going to be an attraction between the negative end of the one magnet and the positive end of the other magnet. And this attraction between the molecules, this IMF, is going to be a polar molecule attracted to another polar molecule. So it's going to be dipole, dipole. And that would be its IMF attraction. Okay, again, let's save these examples for class, and that will be a great way of reviewing this. Hydrogen bonding is an extra strong kind of IMF, okay? And we have to have, it has to meet these two criteria, all right? So in order for a hydrogen bond to occur, one of the molecules, because first off, it's an IMF, so there's got to be two molecules involved. Molecule 1 and then molecule 2, okay? One of the two molecules has to have a lone pair on it. Anywhere on it, it's got to have a lone pair. It doesn't have to be a lone pair on the center. It's just got to have a lone pair, okay? And then the second molecule has to have a hydrogen bonded, okay? Not IMF, but like a bond inside the molecule, a covalent bond. This hydrogen needs to be bonded to fluorine or oxygen or nitrogen. It's got to be one of those. And it's super silly, but the way that I remember this is it's not fun, it's fawn, but close enough, right? We're not having fun, but close enough. So F-O-N. All right. Now, what if we go back and we analyze this one? This is absolutely dipole-dipole. But is it also, in addition to dipole-dipole, is it also hydrogen bonds? Because one of the two molecules has to have a lone pair, and look, this one has a lone pair, and the other molecule has to have hydrogen bonded to fluorine, oxygen, or nitrogen. So this absolutely meets the criteria for hydrogen bonding as well. The IMFs, there's more than one type of IMF between these molecules. One of them is dipole-dipole, and the other one is hydrogen bonds. Okay. So let me give you another one. What about nitrogen, N2, okay, and HF? Okay. Just by the fact that these are two molecules means there's going to be some type of IMF between them. There's going to be some kind of traction between these two molecules. Let's talk about what this attraction might be. So first off, symmetry. If it's just two atoms, two identical atoms, nonpolar, like this is a nonpolar molecule. This one is definitely not symmetrical, so this is a polar molecule. So we don't have dipole-dipole, okay? But do we meet the criteria for hydrogen bonding? One of the two molecules has a lone pair, and the other molecule has a hydrogen that is bonded to fluorine, oxygen, or nitrogen. And so the IMF, one of the IMFs that are between these two molecules is hydrogen bonds. Okay, great. And again, I'm going to save these examples for class to help review and talk through this. All right. Yeah. Now, the last type of IMF that we're going to discuss is the easiest one. It's the best one because it's London dispersion forces, okay? So sometimes they'll just say London forces, sometimes they'll say London dispersion. And then, oh, let me think. I feel like there was another name. Yeah, no. Okay, these like London dispersion forces, okay? And the best thing about London dispersion is it occurs between any two molecules. Okay, occurs between any two molecules. Like, it doesn't matter what they are. Like, they can't be an ionic compound, but if it's a molecule, if it's nonmetals covalently bonded together to make a molecule, any two molecules, that will have London dispersion forces. Okay? And we can give them extra special names, and you might see it on the multiple choice. If you just say London dispersion on the free response, that's absolutely fine. But you might see on the multiple choice that they do two scenarios for London dispersion. London dispersion, there's two types of molecules, right? There's nonpolar molecules and there's polar molecules. So our options are like a nonpolar molecule and another nonpolar molecule, or a polar molecule and another polar molecule. Nonpolar molecules, polar molecules, or one of each. A nonpolar molecule and a polar molecule. Now, reminder, we like to give the nonpolar molecules the label of induced dipole, and we like to give the polar molecules the label of dipole. And so, is there an attraction between two nonpolar molecules? Yes. If there's two molecules, there is an IMF attraction between them. And for all of these, it's going to be London dispersion. Now, if we want to be extra fancy, we could call this one an induced dipole, induced dipole. Induced dipole, induced dipole, because it's a nonpolar and a nonpolar. So nonpolar induced dipole, nonpolar induced dipole. Okay? AKA London dispersion. Now, if it's a nonpolar molecule and a polar molecule, then this would be an induced dipole, because that's our nonpolar molecule, with our polar molecule, which is dipole. So it's an induced dipole, dipole. But again, AKA, it is a type of London dispersion. Now, where I want to clarify is there is London dispersion between a polar molecule and a polar molecule, but we don't want to just call it dipole-dipole, because that's also another type of IMF. So if it's a polar molecule with a polar molecule, I want you to say there's London dispersion and dipole-dipole. Okay, London dispersion and a dipole-dipole. So for two nonpolar molecules, you can just say London dispersion. For a nonpolar molecule and a polar molecule, you can just say London dispersion. But if it's two polar molecules, we're going to have dipole-dipole plus the London dispersion. All right. Last thing. There are two ways that this London dispersion can be stronger or weaker, okay? And so these are the two. The size of the molecules or the atoms, and then the shape, okay? We get stronger London dispersion, like let's do this. The larger the molecule, the larger the molecule, the stronger the London dispersion force. Okay. Okay. Sorry, y'all. I have someone at the door. Okay, let's wrap this up. So the larger the molecule, the stronger the London dispersion. So like if we're comparing C2H2, which is a nonpolar molecule, to C4H, let's see, 6, 10, okay? This is a larger molecule than that one is. So if we have a bunch of C2 molecules, there will be London dispersion between those molecules, but this would be a weaker London dispersion, where C2H4 is a much bigger molecule. So if I have a bunch of these C4H10 molecules, they'd have stronger London dispersions between them. And then the other thing that comes into play is the shape of the molecule. And they usually show you. They usually have something that looks like this. Okay, they'll have some kind of molecule like this, and then they'll show one that's the exact same number and type of atoms. Okay, so we have like the same chain of carbons involved here. Those are all hydrogens. And it turns out that these longer molecules have stronger London dispersion, and these like crowded molecules that aren't pulled out into like long molecules, these ones have weaker London dispersion. So the shape plays a role as well. Long molecules have stronger London dispersion, and like crowded molecules around the center here, this has weaker London dispersion. Okay. Okay. Again, I think I'm wanting to save this for class, but I do want to do like a broad overall review. Okay, go to page 14. Page 14. All right. So, general overview. There are two main types of IMFs that I need you to be aware of, okay? So when we're talking about IMFs, we got two broad categories. One involves an ion, okay? One has an ion with it, and then the other ones only involve molecules. Now, there were two types of IMFs when ions were involved. We had an ion-induced dipole. That was one of the IMFs. And we had an ion dipole. That was the other IMF. And reminder that an attraction between an ion and then the induced dipole is an ion and a nonpolar molecule. So if there was an ion and a nonpolar molecule, then there's an ion induced dipole IMF. Now, if we have an ion dipole IMF, that involves an ion and a polar molecule. Okay? The strength increases going down. Like this is a weaker IMF, this is a stronger IMF. Okay? The strength of these IMFs increase going down. And then the last thing for this side is we will not have multiple of these simultaneously, right? If there's an ion involved, it's one or the other. So there's not going to be ion-induced dipole and ion dipole happening at the same time. It's either ion-induced dipole or it's ion dipole. Now, the second type of IMFs have to deal with only molecules, okay? And so our molecules, there's going to be London dispersion, there's going to be dipole, and then we're going to have hydrogen bonds. Okay? So those are the IMFs when it's molecules, between molecules. London dispersion happens between any two molecules. Okay, it doesn't matter. Any two molecules, there's London dispersion. Now, if they both happen to be polar molecule, so a polar molecule and a polar molecule, then in addition to the London dispersion, there's also dipole, okay? And then the last one is hydrogen bonding. And reminder, for hydrogen bonding, we had two criteria here. The first molecule, one of the two molecules had to have a lone pair on it, and then the second molecule had to have hydrogen bonded to fluorine, oxygen, or nitrogen. Okay, so it is every two molecules will have London dispersion. It might also have dipole in addition to that London dispersion. It might have London dispersion and hydrogen bonding, or it might have all three of those together. Where this one, they're independent. One can exist but not with the other one. All three of these could be happening between the same molecules, or maybe only one is happening between the molecules. There will always be London dispersion if it's two molecules involved. Okay? The strength also increases as we go down. London dispersion tends to be the weakest, then dipole, and hydrogen bonds are the strongest. However, we did talk about when these attractions will increase if the charge increases of the ions, or if the radius decreases for the ions. Those are the ways that we increase these type of IMF attractions. Okay? However, we increase London dispersion not with ions, but the size. Okay, so if we have a larger molecule, then it increases the London dispersion, where if the radius is smaller for the ion, it increases. Smaller radius, larger molecule. All right, a lot of info in this. We're going to go over it in class, and then it's going to show up a lot, and so we're going to spend lots of time practicing this throughout the unit and the rest of the year. Good work, everyone.